However, the includes more general functions, like non-step function, but they can be approximated by step function. The real thing. Okay, so this is also been defined quite well for exercise, people escape, and uh, escape, escape, and partition is of basically a step function, which contains for some subinterval there are n partition. Now the more general function. Say we have some random function like this, or some function like this. We'll suppose now this is called bounded and unbounded, and we'll see why that. So any function, yes, can be approximated and its integral calculated by using the functions. What it basically means is, right, we have some function that has some constant value. So we just maybe approximate one like here, that's probably TOS, and another function here, 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 here. And it must also obey this comparison theorem, where SNX should weigh the comparison theorem. So first you approximate F by S and T. This is below T, below F, this is above. And then this is basic collection of the numbers. And they are related like curve. Sorry, less than X for all X. This is by the comparison theorem. There's a 1.5 in the previous section, I think. And we say this F has to be bounded if it can be approximated by these step functions. Because same here, as you approach zero, y approaches infinity. Later we'll see if it approaches zero plus 0 minus it equals plus or minus infinity. So if you come from also this side, you get plus infinity. But you come from minus infinity, you get minus infinity. So that's one thing you have to know. So basically it has to be bounded, and in most cases people just write it like this. So now we know to some extent a bounded function. It can have some definite value between its interval and doesn't have arbitrarily large values as it approaches some x value. Then we can say at this point we proceed to plan out how we define what an integral is for a bounded function. So definition bounded function. So we define the terms, what we need, what we don't. So as we of function and define the boundary. Define and boundary. That means it will this in this into now let S and T all let first be arbitrary. That means the function also defined in the same interval such that this function is less than equal to the boundary function we actually care about and equal to the greater step function for every x in this interval. Now, second part of there is one and only one number, right, such that this inequality is true for every pair of step functions. That means in that space, every step function you take, no matter what you can come up with, S and T, the higher and lower step function, then I called integral from A to and denoted as how we this should be defined by this. And this integral on now few terms or concept A is less than B. If it is the two, that into and we also know equal 0. This function I could call it integral A and B limit integration. And this integral maybe is called integral integration. So now we talk about upper and lower integral. So first let's just give the and prove 1.9 below with the function f, which we found on this interval we have a lower integral if and upper integral satisfying the inequality. Okay, okay. Lower integral of one integral is equal to t at dx for all step function of t. With f equal to equal to t. Now, we come to the important part. The function f is integral on this interval AB if and only if the upper and lower integrals are equal. That is, if equal to the lower upper, and that should be equal to half integral. So why don't we prove this statement? So let's say we have a function f which is bounded on interval. We also have this step function. Now let this set s be equal to integrand of the step function. So function f is equal to f all possible that and the t equal to the same as the function t. Now we know that the set s and t are not natural. Therefore bounded mean typically t would probably contain some value. Also since f is less than equal to t, which implies integral also less comparison theorem. Therefore, and we also have used stream and beam theorem, which says that given f and t of real numbers or r and f is less than equal to t, this is just a crude presentation of the theorem, assuming the highest value of f is less than equal to t of t, the lowest value of t. I mean the highest low value, and this is the lowest high value. I mean it's not imported only. So therefore we have this by this definition of and by the definition of improvement. This is the definition of here, by the definition of improvement. But we know by the previous theorem of definition that there can be only one integral, then only it is said to be integral. So therefore, but now we have I can be because both of these satisfy the previous inequality with above inequality, which must mean this. So um, that is equal to our integral. So that is now. So you have a low integral in the upper bound or something, or higher the upper bound. Yeah, that's a nice concept. Because, a particle like the upper bound. I mean the highest lower bound. Oops. So we have upper and lower integral of a bounding function there. Now we come to the general function, the area of an ordinate set expressed as an integral. We showed that the area of an ordinate set of a non-negative step function is equal to the integral of the function. Now you'll show that the area of ordinate set of a non-negative function, general function, boundary function is equal to the integral of the function. So first let's state theorem and then we'll prove it. So let us negative option integral to on the interval if p and let q not ordinate set of over in then let then q measurable and equivalent to so simple put say infinity a two regions such that infinity step function such that equals as so step function we all frequently so p equals p. So let now we know that this is integrable on maybe so that's integrated but no chosen as such that then integrate but then we know this just fx of t. Now fx is equal to f equal to p. I mean t. Also, we defined it in such a way that I equal to area. That is which use the ordinance. Next, another theorem which is I think common knowledge that a curve has zero area, but with respect to integration, let f be a non-negative function again. And, and this into graph of f that is the set x y such that if it between that interval and y is equal to fx, which is basically the curve itself. Is measurable and area is zero. The growth is quite simple, but I don't know. In hindsight, I don't understand how this is kind of okay. But let's say let Q denote the ordinary function. Okay, both of the functions, yeah. Now let Q dash be equal to less than. This is an important point. Perfect. So you just remove a curve, basically Q dash. Now, what's the area of Q dash? So you can just say in interval say to B, say we integrate because that is equal to this when integrating the limit. So then we get h now same way we know by area axiom that you can do this that area of an ordinate set so then this is equal to 0. So yeah, okay. This is standard high school stuff. So this basically means rectangle. Say x less than f of a strict here the x less than y. It's decreasing, so it can be greater. And here x actually at that point also, so I feel that's fine. Yeah, for an example, the book gives the example say alpha to integer. Here, let me prove this as induction, say it's one. So then let the main number is greater than zero. Like now here, and also equals to 3. Option. Then there's another example, the square root function. So x is the 1. Two to 1 is that equal to root 3. With the action by to now x is 1 number of plus and the row of plus obviously because square root of the x is for that. Now then simplify this is root of 1. Hold on. This way. More comment. Obviously, this thing should be greater than 0. So if we just draw something like this, obviously 1 minus up to 0. Increase distance from draw. Yeah. Okay, now we come up to the integrability. of a boundary monotonic function. Unique function. So we discuss theorem enunciation. In fact, is monotonic on a closed interval, just interval on that closed interval. Here's the thought. What happens if it's an open interval? Yeah, this human scheming. Yeah, that's very yes. That's very continuous. I'm sure you have to listen. So proof. So monotonic. So that be an increasing function. It's anonymous or decreasing control. If that x came in greater than x k. So in the lower integral, yeah, upper integral, we have it. So let be n be a positive integer. Okay. And now we construct two functions, step function Sn, Tn, and partition such that this partition x0 all the way to xn on this interval AB subinterval is k x1 to xk. Now we make it so that xk and xk minus 1 equals k by n, and every interval is equal to this for our xk minus 1 member of the partition set. So now we define this fn of x was f of xk minus 1, and that's step function for any x accuracy. The n of x f of xk for x between xk and xk minus 1 open interval. This is you change this for this function, decrease function. So s of x is equal to s of x less than equal to k and I. So whether it's an increasing function, and over here xk minus 1, here xk for that x, and then x is in between. It will such it. And also you define f of x, s of x, and t of x at those partition points, that is at x0 to xn. Because here we say it only for the open intervals. Define it so that it's defined continuous probably, and then and tn and interval. So what does that equal to? Well, step function integration f of xk because it's tn, and the interval this is t of n minus equals 1 to n f of k minus 1 and then into. So now we also know also sk and hk minus 1 to b minus k by n. So you can take that out to b minus k by n into this C equals 1 to n, both have the same, with the substitute, I know the word for that, same index. So, good. Okay, but C minus S of K minus 1. Then you use telescoping properties. You know that is right. Yeah, so A, B, C, C, C minus A, C minus B, so C, cancel this, cancel, then you get D minus A. That's basically telescoping property. So you get B minus A by N F of B minus F of A. So let's define C as B minus A. This I'm not clear why the author does this, but anyway, so T of n F of n equals to P by N. We know also that this supreme supremum of this Fn function, that is basically is greater than this, and all and we will have to go into this obviously because all of it is less than that. Similarly, the infimum, okay, same way, the infimum, this is the infimum of T of n will be less than all of that, and since all of T n is less than that, x of n is less than that. Okay, so this we have. So now let's take this here and this here. So this is greater than equal to this. So you multiply by minus 1 and then you add it to this. So you get this minus this. Actually, no, you just add this one equal to right? Minus the lower integral of that. Okay, and we also know that this is less than, so T of n divided on both sides will be greater. So anyway, this is greater than this and this is greater than that. So then, but we know what we know the value of this P by n, and we also know that by area property of the axiom, it should be greater than equal to 0. So 0 less than if that is 0 here, you understand that. We also know that a less than equal to x less than equal to a plus y of n for all n greater than one number of integers. Then if x equals to a. So same way with this difference is x. So then is equal to a, which is 0. Which implies which implies as So we just say this theorem first. Assume f is increasing on the closed interval. So that xk equal to a plus k minus a by n k and the same equals 0 to 1. No, 5. Any number. I think a real number. Yeah, any number probably. We have a complex function, so we have to satisfy. Say notice k equals 0 to n minus 1. Usually it's k equals 1 because they're taking the kth interval. This is the lower step function. And this is the upper step function in standard. This can also be k minus 1, k equals 1 time. For every integer greater than or equal to 1. Then this is if m equals then so let's just prove it first. So Sn standard Sn dn specific approximating step functions. Okay. And in the partition, define on the partition, if you text in on that interval AB. Now that s of n be less than or equal to f of x less than or equal to t of n. So then this interval holds by comparison theorem. Also lets the partition locate subinterval b equal to b minus a by n. So then also that s of x be defined such that this is f of k minus 1 for x in the open to k plus 1 minus yeah, and t of x equal to f of x k. Okay, so we have all our definitions. So then, since this is a step function, this is equal to sigma k equals to 1 to n of k minus 1, and difference x k minus 1 by n. So first we take this out and then we de-index it. Good. Same way for p. You get k equals 1 to n, or you can just write it directly. Equals 1 to n xk. So now we know that from the last theorem, it is there is an increasing function. So since it is an increasing function, it is monotonic. Since it is monotonic, it is integral. But since the same as I defined the function, which we have created. So now AB dx minus that same equal to I minus dx. So 0, but we know that this is less than this, which implies minus Sn is greater than Sf. So since it is greater, you can directly just substitute it. So we have our first side of the inequality. On the other side, or we can just take the same thing here. So AB, then so AB. So this, if you plug in it here, oops. So we have 0. And here, so that's 0 over the dx is equal to, we know this value is equal to c by n, where c is equal to p minus a. P minus x. So then we just say this. Also, we know that for putting in number of, we also know that this theorem is called, this inequality holds on then x equals to a. So similarly here, I minus, so I go, and then we go to the similar theorem for decreasing functions, assume f is decreasing on AB, or it is not assuming it is connection, it is. Then say we have x cube equals a plus e minus a by n scale for each integral a equal to 1 to n. Then any number I will satisfy this inequality. Just notice here it's equals 1 to n. They just give us the index basically. Then like a formula but theorems. So yeah. Exercise 13 of section, I think, like on 10. This one. Exercise 13. You get these results. Yeah. And from that, see where n it will apply n from 1. Just looking at this, you can see this is right. At least before we just take p minus 1 here and then you add obviously that is definitely on maximum. We just take 55. Then from that, we have this much where it's 1 for the result. But here we have 0. K equal to 1 by 0 to the power 2. 0. Everything is inductive. So now you have the number of terms on the left and right side. So now if we multiply this into p by n plus 1. So we have p by n 1 here, k p by 3 so like that. You know k f of x equals x to the power 3 minus k equals p by n and to the k term. K equals 0 1 all the time. And now we say we take a equal to 0 because the previous theorem said that we need some type of a and we take f of x equals x to the power t. Then it follows I p plus 1 b plus 1. Get that? And by theorem 1.13 where we say for increasing function or monotonic function is integrable and get that is integral is equal to that I which satisfies the famous property. of profit in this property develops. Linearity with respect to entry. You can also prove the induction. Yes, okay. Fine. Central basin for all experience. Additivity, additivity with respect to the interval of integration. If n of the three integral is the any three axis of the remaining axis and resolution holds under resolution. poles. Then we have invariant under translation. That is, oh, I forgot to tell you how to prove these. You can prove these with a statement, but you can't prove on it. Just future and okay, don't worry. So I'm going to go on with that. Yeah. So this linearity one. First, you prove this C1 f of x equal to C f of x by creating the two approximate step function. First, we know since it's integral, we don't take C1, we just take the sum Sn fx Tn integral. So, and it exists, that exists. Then you take another integral, the same step function, you get C1 to each. And we know that since the first one exists equal to I, and it's a value. So you multiply C1 to each of these, you get C1 I. But I is f of x T. You see outside, and then integral is also equal to the previous one, C. You can find C1 f of x equal to this. Then for G and thing, first you take separately F, G, prove that it's integrable, C1 F2. Okay. I mean, just F and G. Then you add the two inequalities, you get a new inequality. And since both are integral, hmm, the sum, you prove that the sum is integrable, and then say it's equal to I. Then you say lower thing, infimum and supinum and infimum, and that is equal to each other, and then so it's integrable. So then you integral what is the value using that nearly the same proof. You say it's equal to this sum I, and then you add it, and then that this integral value minus I is equal to 0, and then you say okay, this is equal to I, and that is the integration value for that. And the additivity on is since any two integrals exist, right? So this and this exists. So you just exact same of area. You say this one is zero, then this area exists. Okay, and that area is equal to I. When you say this is equal to something, you take the integral and you prove that this is equal to some sum. You don't know whether it is right. Then you take this I1 something and you prove that it has a value of I1 and this has I2. Then you add it. Then you get the same sum as the right side. It's equal to sum I. So since this exists and it's equal to I1 plus I2 and up, and you do it. Then in making some translation of this one, it's kind of hard. I mean, logically speaking, I'm not sure exactly on how to do it, and the book doesn't even explain what I'm just riffing. You go through say AB, so you create a new function, say Sn from AC to BC, and Tn AC to BC. First you prove that it is integrable. So you go that and you put that low and premium, supreme, because this already exists, right? So every value of this exists, and it's a monotonic function also, because this is monotonic. So we only first prove that it is monotonic, and then you can use the theorem and say, okay, fine, it is integrable. And then what is that value? So then you define two-step function BC. I mean S of n, T of n, and you take it to each value, and then there's nothing. Yeah, and S of n x minus p, T of n x minus p, or you can just say x k whatever. Um, exactly. Yeah, if you like it, use it. But yeah, first you prove that it's integrable, and then you prove that the value of the function. How do you prove that these two are equal? Then for every value of that function here is equal to every value of this function here, and the sum will be equal. This f of s of n x minus e will be equal to this s of n of x for every value for any n greater than this thing, and then you prove that. Yeah, oh man, that was very close. The next one, I mean, even I'm not completely and exactly sure on how to do, but later as the exercise will become clear. Expansion or contraction of the interval of integration. That is, if f is integrable, doesn't have to be monotonic, but you can say if it is monotonic. But generally, they say if it's integrable, you can just take for monotonic function and improve it. But more general, that and for every k, every real k, that is this into which in the theorem say is equal to that. This one first you prove that this exists by taking into approximate step function, and since this exists in every value that exists in this video, this one k first. One k out. It doesn't matter. But you prove that it's integral. Main one is integral. How do you prove that it's equal? Okay. This and this is equal to when you get to sum left side and right side and you minus the sum, so you get 0 less than equal. You'll get to see that the left sum and the right sum cancel out and you get some value. And you say, okay, fine. This value is equal minus this value is some weird relation. And then you will say, okay, fine. That weird relation for every n greater than n clearly means that it's equal to 0. And then if it's equal to 0, that means this value is equal to this value. Simple as that. For the same theorem, put k equals to minus 1. Look at this. It's called reflection property. I'm not sure that it's exactly right. Writing it on my own, someone can factor reflection property. The book says you just replace k with minus 1, but I'm sure. In the last theorem, in this section, not this section, this 1.24 or something, yeah. Yeah. This comparison theorem thing. If then also similarly, if this less than this, employee given the same previous conditions of relationship, but this hard to prove the opposite. Also, note that if g of x equals to 0, integral from g of x is equal to 0, we have for every function, every non-negative function, its integral interval also non-negative.